Hello. So name of the project is Product Matching for E-commerce using deep learning. E-commerce has seen an incredible growth in the past few years, and the transition to e-commerce has further been accelerated by the COVID-19 pandemic. Hence, for e-commerce website, it has become increasingly important to develop high quality search results and recommendations. With millions of third party sellers now joining their websites over the past few years, the process of distinguishing between products have become incredibly difficult. Hence, the goal of this project is to develop an efficient strategy to find similar products available on an e-commerce website by utilizing the product's image and text label. Let's first just begin with one of the live demos. Here we choose the product image. We have selected here Nivea body cream, and for the text label we will just write the basic name of the product, that is Nivea body cream extra white. And when we submit this, we will find all the different products that are similar to the original uploaded product that are available in our database. So these products are being ordered in such a manner that they are being shown in a decreasing order of similarity. Hence, the first few images are extremely similar to the original product images. Hence, all these images can be grouped together. These images can be grouped together, and the best product can be selected from all of these and can be shown as a search result to the user. Whereas the lower ones are either, we can see, as a variations of the original product. As we can see here, this is a variation of the product that is being sold by a different company, or it can be products being sold by the same company, which is Nivea here, regarding a similar topic, where here is it's a face cream for different part of the body. It is a body serum rather than a face cream. So now the similar things can be noticed by the second demo. Here we see for a demo we see an image. Here it is, the image shows a hair tonic which has been created using ginseng and aloe vera. When we try out this example, we can see all the different related products that are available on a website. We can easily notice that some of these products are extremely same to each other and can be grouped together. Some of these products might be being sold by a third party seller, such as this product, and some can be just being sold directly by the company. All these products can be grouped into one single unit, and the best product can be sold according to any sort of metric. It might be the lowest price or the highest discount that is being given to the customers. As we move further down, we see other products. Some of these products can be used as recommendations to the user. Here we see, instead of a hair gel, we see a hair vitamin by the same company, Nature. As we move further down, we see other hair products such as shampoo and conditioners being provided by palm oil, and hair energy sprays provided by few other companies. Since we can easily see how the whole system is working, now let's move to the GitHub repo and understand how it is being implemented and deployed. So as we can see few other examples of how the system actually works and how it is grouping different yet similar products. As we see here is the structure of the web app. The whole web app is deployed on the Google App Engine using a Flask backend and basic HTML, CSS and JavaScript front end. All the data, important data such as model weights, embeddings, product labels are being stored in a Google Cloud Storage, and all the product images are being stored in a Cloudinary CDN storage. We cannot just directly compare the image and text directly at the scale of an e-commerce website. It is incredibly computationally expensive and excessively time intensive in nature. Hence, we use embeddings. Embeddings are nothing special. They are just the vector representation of data by converting the higher dimensional data such as image, text, sound files into relatively lower dimensional data such as tabular data. This allows us to perform much more complex machine learning problems with ease on large inputs. So here we can see the image based strategy. We use one of the pre-trained models on the ImageNet dataset. Here we use an EfficientNet B5, and instead of a softmax layer, we use an arc margin product layer. So why do we use an arc margin product layer? So unlike arc margin product layer, unlike softmax layer, we can explicitly see that feature embeddings generated using the arcface layer is much better because it enforces a higher similarity between the same classes. It is easily seen by this image. As we can see, the softmax images moves away all the different similar class items, whereas in arcface we can see all of them are concentrated into much more similar units of area. These inputs cannot be just used directly by an sklearn framework because due to the huge size of the data that is being available provided to us. Hence, we use one of the open source libraries known as Rapids being created by NVIDIA. Yeah, we use further down, we see the similar strategy being used for text labels itself. Here we take the product text label and use a TF-IDF vectorizer and a pre-trained sentence transformer to generate text embeddings which are merged together later. As we move further down, we see how the prediction is being actually done using cosine similarity and nearest neighbor algorithm, and a merging approach being used for the embeddings. Cosine similarity and nearest neighbors are being used to find similar embeddings to the original data embeddings that we have developed. For the merging strategy, rather than you developing two independent outputs, we merge the embeddings into one single unit and then use kernel and cosine to generate prediction. This is a much better way of doing and finding predictions, is because rather than developing independent predictions, we are merging together predictions to find better predictions that are dependent upon both text and image simultaneously, rather than generating independent embeddings which might be totally unrelated to each other. So the metric that we are using is known as average F1 score. For each data entry, we calculate the F1 score, and the mean of all F1 scores are taken directly. Here is the F1 scores function and how it is being calculated. So for the baseline, we have used p hash, and the baseline score, the F1 score that was being developed, is known as 0.55. and the only image models, when we use only the image models, we develop an average F1 score of 0.72, and for the text only based system, we develop a score of 0.62. And for the grand finale, when we merge all the embeddings and generate the final predictions, we can generate an average F1 score of 0.788786, and for a threshold baseline of 0.55. For further information, you can see my GitHub. Thank you.